Hello all, in this video we will see our first oracle complexity analysis of the classical gradient descent algorithm. For that purpose we will focus only on the constant step size gradient descent. Recall that the gradient descent algorithm takes a step in the direction of steepest descent, which is the negative gradient direction. We will focus particularly on the case of the constant step size algorithm that takes the form xt plus 1 equal to xt minus eta times gradient of f of xt. While in practice we need to choose eta carefully, but for now we will just assume that it is some value that will be determined after the analysis. Eta is an algorithm parameter, so as the algorithm designers we need to specify how to choose it. This is in contrast to the problem parameters L, that is the smoothness parameter, and B, which is the distance between x1 from x star, or the initial distance to the optimum. We begin with stating the required oracle complexity result. Recall that we are operating within the oracle complexity framework, where the oracle gives us the gradient and the algorithm performance will be specified as the number of oracle calls required to reach epsilon close to the optimum solution. So the result is as follows. Under assumptions A1 and A2, which say that f is smooth and convex, the oracle complexity of the gradient descent is order of BL by epsilon, where the step size is set to eta equal to 1 over L. Notice that the oracle complexity is specified in terms of problem parameters L and B. Further, we have specified for what choice of step size this performance is obtained. A very different choice of step size will not result in the same performance. Let us look at the proof. The overall proof outline is as follows. The first step is that we will establish a one-step bound using smoothness and convexity. So this will be a result when going from xt to xt plus 1. Then we will stitch together all the results for all t and carry out a telescopic sum. And the third step will be to show a unique property for gradient descent, which is that the function value is non-increasing, which will allow us to get to the final result. As you would see later, this would often be the skeleton of the proof. Let us begin with the first step, that is using the smoothness and convexity properties. Now we have seen many properties of smooth and convex functions, and ideally you should have them at your fingertips, or at least on a sheet in front of you when you are trying to prove algorithms. So we begin with writing down the update equation, which is xt plus 1 equal to xt minus eta times gradient of f of xt, and then subtract x star from both sides to get xt plus 1 minus x star equal to xt minus x star minus eta times gradient of f of xt. Then let us take the inner product of two sides with themselves. Since we are operating in the inner product space, this is also the norm. So expanding the right hand side, we get norm of xt plus 1 minus x star square equal to norm of xt minus x star square minus 2 eta inner product of gradient f of xt comma xt minus x star plus eta square norm of gradient f of xt square. Next we will need to bound the second term, so let us consider that separately. We will use the following property of smooth and convex functions, which is that f of y is greater than equal to f of x plus inner product of gradient f of x y minus x plus 1 by 2l norm of gradient f of x minus gradient f of y square. If you have attempted the latest assignment, you would have proved this on your own. If not, please do try to prove it on your own, at least for inner product spaces. We will use it with x equal to xt and y is equal to x star to obtain f of x star minus f of xt minus gradient f of xt comma x star minus xt greater than equal to 1 over 2l norm square of gradient f of xt minus gradient f of x star. Recall the optimality condition that says that gradient f of x star is equal to 0. So we can use that here in order to get f of x star minus f of xt minus inner product gradient f of xt comma x star minus xt greater than equal to 1 over 2l norm square of gradient f of xt. Next, let us multiply by 2 eta and rearrange so as to get the bound on the second term that we required. which is a minus 2 eta gradient f of xt inner product with xt minus x star less than equal to minus 2 eta f of xt minus f of x star minus eta by L gradient of xt norm square, which is the bound that we wanted to apply. So let us substitute this bound back into the equation we were earlier considering. Then we will get that the left hand side, which is xt plus 1 minus x star square less than equal to xt minus x star square minus 2 eta f of xt minus f of x star plus eta times eta minus 1 by L gradient of f of xt norm square. Now at this stage you can notice that the second term contains the optimality gap f of xt minus f of x star, and suppose that we assume that eta is less than 1 by L, then the last term, which contains eta minus 1 by L as a factor, becomes negative. So we can drop that entire term because it is negative on the right hand side, and we will have the bound which will be of the form xt plus 1 minus x star norm square less than equal to xt minus x star norm square minus 2 eta f of xt minus f of x star. So in the end we have used the properties of smooth and convex functions. Also we have used the optimality condition of the problem, in other words the definition of x star. So at this stage now we have a one-step inequality or a bound that holds for any t. Now we need to analyze the impact of this one-step inequality on the overall algorithm. So let us keep it ready for now. Next, let us look at the telescopic sum. The telescopic sum is a useful trick that we will often use. The basic idea is that if you have a series of the form a1 minus a2 plus a2 minus a3 plus a3 minus a4 and so on, then the sum is clearly given by a1 minus at. So that is all there is to it. So using this in the one-step inequality that we have obtained so far, we have sum over t from 1 to capital T, f of xt minus f of x star less than equal to 1 over 2 eta norm of x1 minus x star square minus norm of xt plus 1 minus x star square. Recall that the first term was equal to b and the last term is negative, so it can be dropped. So this gives us the result, left hand side less than equal to b by 2 eta. Next we prove the non-increasing function value property. This property is actually true for all smooth functions, convex or not. To establish this, we will use the quadratic upper bound applied to xt and xt plus 1, written as f of xt plus 1 less than equal to f of xt plus gradient f of xt comma xt plus 1 minus xt plus L by 2 norm of xt plus 1 minus xt square. Now substituting xt plus 1 minus xt as minus eta times gradient of f of xt, we obtain that f of xt plus 1 is less than equal to f of xt minus eta times 1 minus eta L by 2 times gradient of f of xt norm square. Remember that we assumed that eta was less than 1 by L, or equivalently 1 minus eta L by 2 is greater than half. So we can use this bound here so as to obtain f of xt plus 1 less than equal to f of xt minus eta by 2 gradient f of xt square. From this we can conclude that as long as the chosen step size is less than equal to 1 by L, the sequence f of xt in gradient descent always decreases by an amount that depends on the norm of the gradient square. This is interesting because near the stationary point, we have that gradient f of x star is equal to 0, so progress is also slower. All smooth functions have this property that even if the step sizes are chosen to be constant, the progress regulates itself when it is close to the optimum, so that if eta is not too large, it never overshoots the optimum. We will see later that this property does not hold when dealing with non-smooth functions, where the gradient or actually subgradient iterations tend to overshoot when near the optimum. So that's why they cannot work with constant step sizes. Finally, also note that the amount of decrease or progress depends on eta. Indeed, larger eta is better provided it is less than 1 by L. So here we have concluded that the sequence fxt minus fx star is non-increasing. To conclude the proof, let us summarize what we have established. We have shown that 1 over t, t equal to 1 to t, f of xt minus f of x star is less than equal to b by 2 eta t, where we have divided both sides by capital T, and that the sequence f of xt minus f of x star is a non-increasing sequence. This means that the last term in the summation is the smallest. So we can upper bound all the terms in the summation with the last term, so as to obtain f of xt minus f of x star less than equal to 1 over t is equal to 1 to t f of xt minus f of x star, which is less than equal to b over 2 eta t. The final step, which is always done at this point, is the proper choice of the algorithm parameter eta. The proof up to this point required that eta is less than equal to 1 by L. Further, if we look closely at the bound, we can see that the bound is the smallest if eta is chosen to be as large as possible. So we should ideally choose eta equal to 1 over L. Now this does not necessarily mean that the choice will make the algorithm faster, only that the performance bound that we have obtained is as small as possible. So we obtain the final performance of the gradient descent after t steps as f of x capital T minus f of x star less than equal to BL by 2t. This bound also translates to the oracle complexity result. Just set it equal to epsilon to obtain that t is equal to BL by 2 epsilon. So this concludes the proof. Observe that in the proof we have used all the assumptions. We have used the smoothness twice and used convexity property in the first step. We also used the definition of x star, that gradient f of x star is equal to 0. So in general, if you prove anything, you should always verify that you have used all the assumptions. If not, either something is wrong or that assumption which you have not used is really not required. So that is all for this video. We are done with our discussion of the basic version of gradient descent. The subsequent videos will consider more advanced versions. The next video will take a close look at the selection of step sizes and some strategies to do this selection automatically.